When taking a limit, the first thing we do is plug in the value and see what happens. If we get a number, we're done. If we get 0 over 0, we need to factor, conjugate, or expand. What if we get a number over 0? In that case, the limit will be infinity, negative infinity, or does not exist. To determine which, split the limit to be from each side and evaluate separately. Evaluating one-sided limits when you get 1 over 0 has its own special rules. First, this will always exist. It will be infinity or negative infinity. To determine which, think of a number a tiny bit smaller than your limit. In this example, that would be any negative number. The numerator is 1, which is positive, and the denominator would be negative. Positive over negative is negative, so this limit is negative infinity. From the other side, think of a number a little bigger, in this case a positive number. Then it becomes positive over positive, so the limit is positive infinity. These two values don't match, so the original limit did not exist. Here's a picture of 1 over x. You can see the limits. From the left, the function goes down as it approaches 0, and from the right it grows. Here's an example of a function that has a limit of positive infinity at a. Both sides are growing towards infinity. Notice the vertical asymptotes. That'll always happen. Here's another example. The limit is x goes to 2 of x minus 3 over x minus 2 squared. Plugging in 2, we get minus 1 over 0, so we need to split this up. From the left, think of a number a tiny bit smaller than 2. If you like, make it 1 or 1.5. The top will be negative and the bottom positive, making the overall expression negative. The limit is then negative infinity. Next, from the right, take a number a little bigger than 2, but be careful. If your number is too large, it'll change the sign of the top, which we don't want. Try to think about 2.5 or 2.1. Don't worry about not being able to get the exact number, we only care about the sign. The top will be negative and the bottom positive, so the limit is again negative infinity. Both sides give negative infinity, so the overall limit is negative infinity. So far, all of our limits have been as x goes to a number. What does it mean if x goes to infinity or negative infinity? Horizontal asymptotes. This picture is a demonstration. Notice, as x gets large, the function is getting closer to L, and as x goes negative, the function is getting close to M. How do we actually evaluate these? Let's do an example. The limit is x goes to infinity of 1 over x. This means x is getting huge. Think about taking 1 over a huge number. For example, 1 over 10,000 is small, and 1 over a trillion is super duper small. 1 over the largest number you could possibly think of would be minuscule, so the limit is 0. Obviously, this example is simple, but in a way, it's the only thing we use. Here's the next example. This is far more complex. Let's approach it like a typical limit. We try to plug in the limit and run into an issue. We can't plug in infinity, that doesn't make any sense. But this does tell us to do something else. We have a polynomial over a polynomial. Multiply the top and bottom by 1 over the highest power on bottom. It's important that you use the highest power on bottom. In this example, the highest power on bottom is x squared. Multiply the top and bottom by 1 over x squared, distribute this through, cancel. We basically get our first simple example several times. As x gets large, 3 stays the same, 3 over x goes to 0, and 4 over x squared goes to 0. Similar with the bottom. Finally, we're left with 3 over 2. There are rules for problems like this, but they don't always work. You'll encounter examples where your only option is the method I just described. There are a few functions you should know something about. First, the natural log of x. The graph looks like this. Notice ln of 1 equals 0, and as x gets large, the natural log gets large, and it goes to negative infinity as x goes to negative infinity. Second, arctangent. This has horizontal asymptotes at pi over 2 and minus pi over 2. Finally, exponentials. They act almost the opposite of the natural log, because they are. Notice the domain of natural log is x greater than 0, and the range of the exponential is y greater than 0.